Welcome again. In this video, I'm going to talk about nanosatellite integrated with microfluidics. This is nanosatellite, and these are microfluidics. First, I'm going to talk about microfluidics, and then in the next slide, I will talk about nanosatellite. These are microfluidics, and the microfluidic is a small device to handle small quantity of fluid passing through channels having microscale dimensions. And to move the sample or the liquid in these channels, an external pressure is applied. This is contrary to digital microfluidics, as I introduced in my previous videos. Small droplets are manipulated between two conductive plates coated with the electric layer and hydrophobic layer by applying electric voltage. It is an automated movement of a discrete droplet. And the satellites are normally defined according to their weight. 0 kilogram, 1 kilogram, 10 kilogram, 100 kilogram, and 1,000 kilogram. And the so-called CubeSats are designed according to their specification. They have a design specification. 1U from 1U to 12U, and 1U 10 centimeter, 10 centimeter, 11.35 centimeter, and the weight is less than 1.33 kilogram. This is the unit, the so-called CubeSat standard. These small boxes can contain all the primary system that large satellites have. Due to its simplicity, the design was very popular. Eventually, CubeSat became widely adopted as the standard. What is the application? First, we have Earth observation or remote sensing. Second, you have communications. Third, you have it can be applied in scientific field, in technology, and some other application. Earth observation takes the biggest part. The majority of CubeSats today are devoted to Earth observation, notably from the commercial companies, followed by communication. Communication takes 27%, and Earth observation 41%. It seems that in the coming years, these two categories will still dominate, although we can see the growth in scientific field, 10%. Scientists came up with the idea of integrating nanosatellite with microfluidics to study life conditions on Mars. That experiment consists in placing a lab-on-a-chip microlaboratory with a small grain of control plant on board the nanosatellite. During the flight, they expect the grain to freeze in the atmosphere. Then, after increase of temperature, and the seed will be irrigated. The scientists will check if and what force it germinate, as well as how the roots develop. The mission is not easy, because even minimal changes in the gravitational condition can affect the flight. Scientists designed and fabricated a micropod payload for a nanosatellite mission, allowing for the cultivation of grain in space. And this micropod has microfluidic part. This is the design of micropod, and this is the device. In this design, and as well as the device, you have part 1. This is a camera chip. Part 2, LED autofocus housing. LED meaning light emitting diode. 3, microport detection module frame. 4, 3D printed microport. 5, microfluidic peristaltic pump. 6, microfluidic tube. And 7, a Pandolf fluidic connector. And 8, a Pandolf enclosure. This microport payload has to be integrated with nanosatellites during the mission. And this is an example of the flight support and integration of the nanosatellite. And the next video is an example illustrating the mission of launching nanosatellite. Thank you.